Welcome to the deep dive. Today, we're digging into a really great source. It's an excerpt from the 3 Blue 1 Brown YouTube channel, and it explains large language models. We use these things all the time now, chatbots, AI assistants. They feel kind of like magic, but what's really going on inside? So our mission for this deep dive is to use this source, this really clear explanation, to unpack the core mechanics. How do they actually work?
Exactly. And this source does a fantastic job. It takes you step by step, starting with the most basic idea and building up to the pretty sophisticated architecture behind them. It's definitely a complex topic, but getting a handle on the basics, it can genuinely change how you think about AI.
Okay, let's try and unpack this then. Imagine you've got, I don't know, a movie script maybe, a scene between a person and an AI, but the AI's lines are missing.
Hmm.
And you have this powerful machine that can just look at text and predict the next sensible word. What could you actually do with that?
Well, that's pretty much the core idea right there. As the source explains it, a large language model is essentially a very complex mathematical function. Its whole job is to predict the most likely next word for basically any piece of text you give it.
And it doesn't just pick one word, does it? That's key.
No, that's right. What it does is it assigns a probability, like a score, to all the possible words it knows. So imagine this huge vocabulary list, and each word gets a score based on how likely it is to come next after the text it's just seen.
Right. So when you're chatting with, say, an AI assistant,
Huh.
this is exactly what's happening.
Pretty much, yeah. You type your message, that's the input text. The model looks at it, runs its prediction for the next word, picks one based on those probabilities, adds it to the text, and then does the whole thing again, word by word, building the response.
Okay, but hang on. If it's just picking words based on probability, how come the answers sometimes feel, I don't know, creative or a bit unexpected?
Ah, good question. The source points this out too. To make the output feel less robotic, less predictable, there's often a bit of randomness introduced. So instead of always picking the single word with the absolute highest probability score.
It might pick a slightly less likely one sometimes.
Exactly. It sort of rolls the dice,
Yeah.
weighted by those probabilities. It might pick the second or third most likely word, or even something further down the list just occasionally.
Okay, that makes sense. So the underlying math, the model itself, is deterministic, it's fixed. But because of this random sampling element,
Right.
the same prompt, the same input can actually give you a different answer each time.
Precisely. It helps make the conversation feel more natural, less like you're talking to a machine that just gives the single best answer every time.
So how does this machine learn to make such good predictions in the first place? Where does that ability come from?
Yeah, this is where the large part of large language model really kicks in. It learns by processing an enormous amount of text data.
Enormous feels like an understatement here, based on the source.
It really is. We're talking vast quantities, usually scraped from the internet websites, books, articles, code, you name it.
The example the source gave for GPT-3 was just mind-boggling. If a human read nonstop 247,
It would take over 2,600 years just to read the text GPT-3 was trained on.
2,600 years.
And newer models. They've been trained on much, much more data than that. It's almost impossible to really wrap your head around the scale.
Wow. Okay, so it sees all this text. How does it learn from it? What's the mechanism?
Well, the model has these internal values, billions of them. They're called parameters or sometimes weights. You can kind of picture it like a giant machine with billions of tiny dials or knobs.
Billions.
Yeah, hundreds of billions in the biggest models. That's what makes them large. And learning is essentially the process of tuning all those knobs.
And nobody sets these by hand,
Well,
obviously.
definitely not. They start out random, which
Ugh.
means at the very beginning, the model just spits out complete gibberish. Then the training process begins. It's shown example after example from that huge data set.
How does that work? Like, what's an example?
Typically, you take a chunk of text from the training data, maybe a sentence or a paragraph. You feed most of it into the model, like everything except the very last word. Then you ask the model,
Yeah.
okay, predict the next word.
And it gives its probabilities for all the words it knows.
Right. Then you compare the model's prediction to the actual word that came next in the real text example. And based on the difference, the error, there's this algorithm, it's called backpropagation, a really core concept in machine learning that figures out how to adjust all those billions of parameters.
Just a tiny nudge for each one.
A very tiny nudge for each parameter, for
Right.
each example. But the tweak is designed to make the model slightly more likely to predict the correct word next time for that kind of context
Hmm.
and slightly less likely to predict the incorrect ones.
And you do this billions, trillions of times.
Trillions, yes, across all those text examples. And slowly, painstakingly, the model starts to get better. Not just at predicting the words in the text it's already seen, but crucially at generalizing. It starts making reasonable predictions for new text it hasn't seen before.
Because it's learned the underlying patterns of language, the grammar, the facts, the reasoning, all just from predicting the next word.
That's the incredible part. But, as you can imagine, doing this calculation, comparing the prediction, calculating the error, adjusting billions of parameters, trillions of times, takes an absolutely staggering amount of computation.
The source had another number for this, didn't it?
It did, a striking one. If you could perform 1 billion additions and multiplications every single second,
Which is already fast.
incredibly fast, even then, training one of the largest models would still take something like 100 million years on that hypothetical super-fast single computer.
100 million years. Okay. That explains why you need massive computer clusters and specialized hardware.
Exactly. Which brings us to GPUs, graphics processing units. They're essential because they can do many, many calculations in parallel, all at the same time. That's the only way this becomes feasible in months rather than millennia.
Right. But this whole process you've described, this initial phase, the source calls it pre-training.
Yes,
And the goal there was basically just learning to autocomplete random text found on the internet.
that's right. It's learning the patterns of language in the broadest sense.
But that's still quite different from being, say, a helpful AI assistant that answers questions safely and usefully.
Very different goals, and that's why there's usually another crucial stage of training, especially for chatbots like ChatGPT or Claude.
Okay, what's that?
It's often called fine-tuning, and a key technique is reinforcement learning from human feedback, or RLHF.
RLHF. Okay, so humans get involved now.
Yes, this is where direct human guidance comes in. People, human labelers, interact with the model. They might get two different answers to a prompt and choose which one is better. Or they might rate responses based on criteria like helpfulness, honesty, or whether it's harmful or biased.
And this feedback is used to tweak the model further.
Exactly. This feedback is used to further adjust those parameters, rewarding the kinds of responses humans prefer and penalizing the ones they don't. It's a critical step for alignment, trying to make the model's behavior match what we actually want it to do, beyond just predicting the next word.
Got it. So pre-training learns language. RLHF makes it helpful and safe.
That's a good summary. Now, going back to the computation and the hardware, you mentioned parallel processing being key.
Yeah, the source said that before 2017, models mostly process text word by word sequentially, which sounds slow.
It was a bottleneck.
Yeah.
And then came this paper from Google researchers in 2017 introducing the transformer architecture.
The transformer. That seems to be the foundation for most modern LLMs.
Absolutely. It was revolutionary precisely because it enabled massive parallelization. It doesn't read word by word. You can kind of look at the entire input sequence, all the words simultaneously, soak it all in at once.
How does it do that? How can it process everything in parallel?
Well, the very first step is interesting. It takes each word, or sometimes parts of words called tokens, and converts it into a long list of numbers.
Numbers.
Yeah, a vector, a long list of numbers. Because all the math that follows, all that parameter tuning, it only works on numbers, on continuous values.
Yeah.
So somehow, this list of numbers is meant to represent the meaning of that word or token.
Okay, so words become these numerical lists, these vectors. What's the magic that lets them be processed together?
The core mechanism in the transformer is something called attention, or more specifically, self-attention.
Mm.
You can think of it as a way for all these word vectors in the input sequence to talk to each other, all at the same time in parallel,
And talk to each other how?
through mathematical operations. Essentially, each word vector looks at all the other word vectors, including itself, in the sequence. Based on how relevant those other words are to its meaning in this specific context, it updates its own vector. It pulls in information from the others.
Ah, like the bank example the source used.
Exactly like that. The initial vector for the word bank might be kind of general, but through the attention mechanism, if the word river is nearby in the sentence, the bank vector will interact strongly with the river vector.
And update itself to represent riverbank?
Precisely. Or if the word money is nearby, it interacts with that one and updates itself to represent financial institution bank.
Huh.
So attention allows the meaning of each word, represented by its vector, to become context dependent. And it happens for all words simultaneously.
Okay, that's clever. So the vectors refine their meaning based on context, all in parallel.
Right. And transformers usually stack these attention layers multiple times, so the vectors get refined again and again. They also typically include another component in each layer, usually a feed-forward neural network.
What does that do?
You can think of it as adding more capacity for the model to learn and store general patterns about language during that huge pre-training phase. It processes each word vector independently after attention has mixed the contextual information.
So data flows through attention, then this feed forward bit, then more attention, more feed forward, many times.
Exactly. Many layers deep. Each layer hopefully enriching those word vectors, packing more and more relevant information into them, all geared towards that final goal,
Predicting the next word.
predicting the next word. At the very end of the transformer, there's a final step. It takes the vector associated with the last word in the input sequence, which by now has been influenced by all the other words through attention and processed through all the layers, and applies a final function to convert that rich vector into the probability scores for every possible next word.
Wow. Okay. So the researchers designed the architecture, the attention layers, the feed forward parts, how they connect.
Yes, the framework.
But the specific knowledge, the ability to write a poem or explain a concept, that emerges from tuning those billions of parameters on all that data.
That's the crucial point. The specific behavior isn't directly programmed in. It's an emergent property of the training process acting on that architecture.
Which, as the source notes, leads to a bit of a puzzle, doesn't it?
It does. Because the behavior emerges in this incredibly complex way across billions of interacting parts, it's often extremely difficult to look at a specific output, say a particular sentence the model generated, and pinpoint exactly why it chose those specific words in that order.
We can see the architecture, we know the training process, but the detailed internal reasoning, if you can even call it that, is often opaque, a black box.
Largely, yes. There's a whole field called interpretability research trying to understand this better, but it's a major challenge. We see this amazing fluency, this capability.
But the why for any specific prediction can be really hard to nail down.
It's one of the fascinating frontiers of this technology.
Okay, phew. That was quite a journey through the source material. We covered a lot.
We definitely did.
We started with that fundamental idea. LLMs as next word predictors, assigning probabilities, and using randomness for naturalness.
Right. Then we talked about the sheer scale, the absolutely massive data sets needed for training, the billions of parameters being tuned.
And the mind-bending amount of computation involved, only possible because of parallel processing with GPUs.
Which led us to the transformer architecture, the key innovation enabling that parallelism through vectors and the self-attention mechanism.
Yeah, that idea of words as numbers talking to each other to understand context.
And we can't forget the second stage, that crucial fine-tuning with human feedback, our LHF, to make them more helpful and aligned.
Definitely. And we finished on that slightly unsettling idea that the specific behavior is emergent, making the exact reasons behind an output kind of a mystery.
So, for you listening, when you interact with these tools, hopefully understanding these core concepts, prediction, scale, parallel processing via transformers, attention, the training phases gives you a much clearer picture of what's actually happening under the hood.
It really does put it in perspective. And it leaves us with that final thought from the source, really. Given this intricate architecture, all this data, all this computation, why that specific word next?
The fluency is undeniable, often remarkable. But the precise chain of reasoning inside those billions of parameters, that remains a really fascinating open question.
And if this discussion made you curious about the nitty-gritty, especially how attention really works mathematically.
Our source, 3 Blue 1 Brown, actually has other videos that dive even deeper into visualizing those mechanisms, so there's always more to explore if you're interested.
Absolutely. Well, we hope this deep dive has given you some valuable insights. Thanks for joining us, and until next time.